So this is Kelvin Mapalo, one of the reporter of test of parallel flow and counterflow heat exchanger. So this would be a report test of parallel and counterflow heat exchanger. So my the report that um, I'm reporting now is the difference in counter and parallel flow heat exchanger. So um, Hatajersen is the first, so you know what is heat exchanger is. So um, now I'll report what is the parallel flow or co-current heat exchanger. So in a parallel heat exchanger, the hot water and the steam flow in same direction. So parallel, that means same direction. And yes, the hottest steam and the coldest water enter the exchanger. At one end, and the cold steam and the heated water exit out the other end. So that's how the parallel flow works. Heat is transferred from the warm fluid through the wall of the inner tube, so called heating surface, to the cold fluid. A heat exchanger can also be operated in counterflow, in which the two fluids are in parallel but opposite direction. So that's the second flow I'll be telling. So that's how the parallel flow works, and this is how the counterflow or countercurrent heat exchanger works. So in a counterflow heat exchanger, the two media or the two fluids are flowing in opposite direction. So they flow in opposite direction, but that's it. So the hottest steam enters on the left side and the hot water exits on the left side. So while the cold steam exits on the right and the cooler water enters to the right. So that's how the counterflow or countercurrent heat exchanger works. So these are the pros and cons on parallel and um, counterflow heat exchanger. So if the designs of two systems are identical, the counterflow type exchanger can transfer more energy than the parallel design, because the exit temperature of the cooler water can get close to the highest temperature of the steam. So that's how the counterflow um, heat exchanger works better than parallel design. So parallel flow heat exchanger undergo a lot of thermal stress because of the extreme temperature difference at the entrance to the device. Parallel heat exchangers are best suited when the goal is to bring the two fluids to the same temperature. So that's how the parallel heat exchanger is better for counterflow. So if you want the media to have the same temperature, use the parallel heat exchanger. So and if you want the hotter media to become cold or to lower the temperature, use the counterflow because it is more suitable in that way. And next is figure represents the direction of fluid in the parallel and counterflow exchanger. Under comparable conditions, more heat is transferred in counterflow than parallel flow exchangers. The temperature profiles of the two heat exchangers indicate two major disadvantages in parallel flow designs. So the large temperature difference at the ends causes large thermal stresses. So here, um, this is the parallel flow and counterflow. So here, the hot fluid and the cold fluid enters at the same time. The cold fluid enters here and exits there. The hot fluid enters here and exits there. So the large temperature difference at the ends causes large thermal stress. So dito um, masyadong it has a large thermal difference which can cause damage to the heat exchanger or yes. So the temperature of the cold fluid exiting the heat exchanger never exceeds the lowest temperature of the hot fluid. So here the fluid does not reach the desired or the lowest temperature because it is flowing parallel. So on counterflow it might because the kasi sinasalubong ng mainit na malamig na tubig yung mainit na fluid which is more efficient. So the design of parallel flow heat exchanger is advantageous when two fluids are required to be brought to nearly same temperature. So that's the advantage of the parallel flow design. Parallel flow heat exchanger to brought to nearly same temperature. So this is the co-current or parallel flow, and this is the concurrent or countercurrent or counterflow. This dito makikita natin in this diagram nearly same temperature, and here the colder become hotter and the hotter become colder. So that's the explanation on the difference of parallel flow heat exchanger and counterflow heat exchanger. So next, we had major components of heat exchanger, different parts of heat exchanger and uses of each. So the first is shell. Shell is the costless part of heat exchanger. Shell diameter depends on tube bundle diameter. As per tema, shell size range from 6 inches to 60 inches. Standard pipes are available up to 24 inches size. If shell size is greater than 24 inches, it is fabricated by rolling a plate. So shell is the main body or the main frame of the heat exchanger. It is where the other part is gathered. Next, shell side pass partition plate. So shell side pass partition plate is not provided to improve shell side heat transfer coefficient, but it is provided to avoid the unfavorable temperature difference or to avoid the cross temperature between hot fluid and cold fluid. So this is the picture of the shell side partition plate, and it is how it works. So baffles are used in shell to direct the fluid stream across the tubes to increase the velocity of shell side flow, and thereby to improve the shell side heat transfer coefficient. Baffles indirectly support the tubes and thereby reduce the vibration in tubes. So next is tube size range from 1/4 inch to 2.5 inch to 2.5 inches in shell, and tube heat exchanger. Thickness of standard tubes are expressed in BWG. Birmingham wire gauge. So tubes are it is where the fluid flows and it can withstand a high temperature. So tube side pass partition plate. Tube side passes are provided to decrease the tube side flow area and to increase tube side fluid velocity, thereby to improve the tube side heat transfer coefficient at the expense of pressure drop. So this is how the pass partition arrangement. um, Later we would see how does pass partition arrangement are arranged. And so next is the tie rods. Buffers are supported by tie rods. Tie rods are made from solid metal bar. Normally, 4 tie rods are required to support the baffles. So, and diameter of tie rods is less than the diameter of tube. So this would be the tie rods. Next is the spacers. Spacers are used to maintain the space between baffles. Spacers are passed over the tie rods, and because of them, baffles do not slide over tie rods under the effect of force of fluid. So tube sheet, so in spacers, if you know the working principle of the spacers using tiles, putting tiles, the the cross, um, putting between the tiles is the spacers, and that's how the spacers on heat exchanger also work. And tubes and one end of tie rods are attached to tube sheets. Hence, entire load of tube bundle is transferred to one or two tube sheets. Tube sheets. It is where the sinusoksok yung mga tubes. Next is the sealing strips. Sealing strips reduce the amount of bypass streams of shell side fluid flowing through the clearance between shell inside diameter and tube bundle diameter, and thereby improve the shell side heat transfer coefficient. So this would be the sealing strip. Yes, sealing strips also make the removal of tube bundle from the shell easy. Hence, they are also known as the sliding strips. Next is the expansion joint. Expansion joint is used in fixed tube heat exchangers to permit differential thermal expansion or contraction between shell and tubes. If expansion joint is not provided in fixed tube, heat exchangers, then fixed tube sheet does not permit the unequal expansion and contraction between shell and tube, and it can result in the development of thermal stress. If thermal stress is higher than permissible value, then it may develop a crack in tube sheet and can result leakage. So this would be the some this would be the pictures of some expansion joint, and this is how it works. Here, flat plate, flange only heads, um, flared shell or pipe segment. Later we would see how does this works, and later we would design one of these. We would design one of heat exchanger, and that's how it is.